Okay, welcome to lecture here. Just give me a sec here to get everything set up. Go this way. All right, go ahead and type here in the chat box. Okay, so we've been talking about bonding and one of those chapters, chapter 3, I think it is. There it is. And we left off talking about formal charges after we talked about how to draw Lewis structures. Remember that when you draw Lewis structures, you do want to make sure that you follow those sort of steps that we talked about. If you follow those steps, you should hopefully end up with the correct structure when it's all said and done. Again, you don't want to draw them sort of in piecework, kind of each individual Lewis dot symbol, and then try to figure out again how they all kind of come together and stuff like that, because usually you'll end up with a picture that has the wrong number of bonds, too many electrons, and things like that. So remember, you want to make a single bond from the center to each of the outside ones. You want to put all the rest of the electrons, starting with the outside atoms and pairs, until you essentially fill up all the outside atoms. And then if you still have electrons left over, you could go to the center atom there and then put those electrons on as dots. When you're all distributed, all your electrons, then you can make sure that everybody's met the octet rule, except for hydrogen that only needs obviously 2. If they don't, then really that's the time when you want to try to do a double bond or a triple bond to sort of fix it. As we talked about, in a lot of cases, you don't usually want to kind of jump right out of the box, double bonding things, triple bonding things, and stuff like that. So you want to make sure you sort of place everything correctly and then kind of use that to fix any type of problems that may occur. Now, we sort of finished up talking here last time about formal charge, and formal charge is essentially the charge each atom would have in that particular structure if essentially all the electrons were sort of transferred. And the way we calculate formal charge is we take the number of valence electrons in the free atom or free element minus the number of non-bonding electrons. So when you look at your Lewis structure there, it would be the ones with the dots, and minus 1/2 the number of bonding electrons, which from your Lewis structure would be the ones with the lines. And that'll give you the formal charge of kind of everybody that's there. Now, sort of one practical application of formal charge, which we'll talk about here in just a second, is that it can help you sort of decide between perhaps two different structures, which structure might be a better structure, which one might be a kind of a worse structure. So that is, so here we did ozone last time. So why don't you, why don't you calculate the formal charge on each of the elements in this particular one here? So the carbon and the 3 oxygens. So why don't you take a moment and make sure you know how to calculate it, and then we'll talk about it. Okay, so let's take a look, see how we're doing. So remember, we're calculating the formal charge. We'll start with something to write, maybe. So we'll start with the single bonded oxygen. So this will go for each of the ones on each side. So we start with the number of valence electrons, which is 6, minus the number of non-bonding electrons, which in this case would be 2, 4, and 6 as well. And minus 1/2 the number of bonding electrons, which would be that line there. And that represents 2 electrons. So that is 6 minus 6 minus 1 gives you a -1. So this oxygen here has a -1 formal charge. This oxygen here has also a -1 formal charge. Now, if we look at the double bonded oxygen, again, we would start with 6, which is the number of valence electrons in the free element, minus, in this particular case, 2 and 4 non-bonding electrons, minus 1/2 the number of bonding electrons, which is 2 and 4 as well. It's a lot of math there. That's 6 minus 4 is 2 minus 2, it looks like. So that is 0. So this double bonded oxygen has a formal charge of 0. We look at our carbon coming in, something like this. Carbon's number of valence electrons, we'll go with 4. Minus, there's no dots, so 0. Minus 1/2 of bonding, which is 2, 4, 6, 8, 2 for each line, gets us 0 as well. So the formal charge here for carbonate, double bonded oxygen 0, carbon 0, the -1 on each of the single bonded oxygens. And by the way, that is really where the -2 comes from in something like carbonate. Again, the 2 oxygens kind of holding a -1 charge each gives you the overall charge there of -2. Any questions on that there? So obviously you do need to know how to calculate the formal charge for any guy. Yeah, so when you do calculate the formal charge, they all should add up. When it's all said and done, all their formal charges should probably add up to the overall charge in the ion, if it is a charge. So like here, each of the oxygens had a -1. So if you add them together, you get a -2 overall. When you're calculating formal charge, you kind of assume that each of the atoms are neutral in that sense. So you don't have to worry about anything in terms of the charge or anything like that when you do formal charge. But when you calculate the formal charge for everybody there, they should add up to the overall charge in the ion. Or obviously, if the guy is neutral, they should add up to 0. By the way, if they don't for some weird reason, then that probably means you made a mistake or it's really a bad Lewis structure. But definitely they should add up to the overall charge, R0 if it's neutral. But when you're calculating the actual formal charge, you don't have to worry about anything about the charge. Yeah, the number of non-bonding electrons are the dots in your Lewis structure, right? So all these guys that are dots, they are non-bonding electrons. So when we take this number here, for example, this is the number of valence electrons from the periodic table. So oxygen is group 6. This is the number of our non-bonding electrons, which again are these dots. So 1, 2, 3, 4, 5, and 6, right? So those are the dots that are around it. And then this is the number of bonding electrons. Again, each of these lines, I'll just draw dots, represents 2 dots. So that would be the 2 electrons that we find there. Other questions on that? Okay. So let's talk about sort of formal charge and really more the sort of practical application of sort of calculating the formal charge. And really sort of the practical application of calculating the formal charge really does have to do with helping you decide, again, between maybe 2, 3, however many Lewis structures you might be able to draw. So as we drew some of those Lewis structures, we saw in certain cases, or maybe in your own head as you were doing some of them, you're like, why could I not perhaps move this atom over here? Or why could I not perhaps make a triple bond versus single bonds, or a double bond versus some single bonds and stuff like that? So we can oftentimes use, like I said, formal charts to help us decide, between different sort of Lewis structures, what might be the more better. That doesn't sound good. The better version, I guess, of a Lewis structure. And here's some of the general sort of rules that you could use to help you do that. If you have a neutral molecule, a Lewis structure with no formal charge is pretty much preferred. So if you could hit pretty much zeros everywhere as you calculate the formal charge, that's sort of the best situation to have. If you have structures that have really large formal charges, like 2s and 3s, that's probably less plausible of a good structure. So it's probably not the best structure. So things that are holding really large positive formal charges, negative formal charges, usually would indicate that it's probably not the best situation. Yeah, we'll calculate it in just a second. Yeah. Now, when sort of choosing between, when choosing among sort of different Lewis structures, we want to, when we sort of have equal distribution of sort of the charge, if you will, we want to have pretty much the more negative formal charge on the more electronegative atoms. So if you got two structures where kind of similar in terms of numbers of the formal charges, you want to look at the actual atoms, and again, you want the more negative formal charge to end up on the actual more electronegative atom. So let's take a look at sort of an example here. So if we have something like CH₂O, here are really two possible ways that perhaps you could put this guy together. And we want to sort of use formal charge here to try to figure out what might be a better structure of the two. So why don't you first calculate the formal charge of each of the elements in each of these guys, and then based on the formal charges that you calculate, try to figure out which one would be the better structure of the two. So take a couple of minutes or so here. Again, calculate the formal charge in everybody, and then try to figure out, based on that, which one you would expect to be the better structure. Okay, so let's see how we're doing. So again, if we go through and sort of calculate some of these formal charges, we'll start with this guy here on the left. If we do our hydrogens, which sort of look like this, that's going to be 1 minus 0 minus 1/2 of 2. Again, no dots, obviously, on hydrogen. One bond coming in, which are 2 electrons, and that's going to give us 0. So this hydrogen has 0. This hydrogen, which would be identical to it, obviously has 0. If we do our carbon that's there, so our carbon looks something like this. In this case, we have 4 for carbon minus our 2 non-bonding electrons here, minus 1/2 of our 2, 4, 6 electrons there. And that's 4 minus 2, which is 2, minus 3 is -1, if I'm not mistaken. And our oxygen, which looks something like this, we have 6 minus 2, our 2 here. Then we have 2, 4, 6 minus 1/2 of 6. And that gets us +1, I believe. So 6 minus 2 is 4, minus 3 plus 1 in this particular case. So for the structure on the left, we hit 0, -1, +1, and 0. Now, if we come to the guy on the right, these hydrogens, by the way, will end up the same as what we just did here on the left. Our double bonded oxygen will also end up similar to what we did before. So 6 minus 4, again, 4 electrons here, minus 1/2 of 4, and that's going to be 0 here. And our carbon in the middle, which sort of looks like this, has 4 minus 0, minus 1/2 of 8, and that is 0 as well. So here we have 2 structures that you could have drew for formaldehyde. Again, following sort of all the rules for drawing things. And based on formal charge, you should hopefully know that this guy here would be the better structure of the two for a couple of reasons. First off, we hit zeros on everything, which is sort of your best situation in terms of a structure. Second, when we look on the left there, obviously we don't have zeros on everything. We have ones, which is, not too terrible per se to end up with ones. But now that we look at that, we do have ones on the carbon and we have 1 on the oxygen. And when we look at the ones that we have -1 on carbon and +1 on oxygen. So if you remember, one of the things that is not the best situation is if you have the more negative formal charge on the least electronegative atom. So because oxygen is more electronegative, we would hope to have had the negative formal charge on the oxygen rather than the carbon. So that also makes that structure on the left not so desirable because our more negative formal charge ends up on the least electronegative atom there between the two. So these are the things that you kind of use formal charge for when you have maybe a situation where like, well, maybe I could draw this structure or that structure. You can kind of use it to help you decide sort of which one might be the better structure. So there's sort of levels, if you will, and like I think the lab coming up will sort of classify it sort of like this, like this is the best, this is like best structure, this is like a better structure, this is like an okay structure, this is like probably not the best structure. So again, you could kind of use formal charge to help you decide those things. Any questions on that there? So when we look at a couple more examples here of doing that, let me just kind of clear off some space here. So why don't we do, okay, so why don't we do the CO2, carbon dioxide. So you're good on that one, we don't need to go through it. Okay, so why don't you do the formal charge on each of these and again decide which one would be the better structure. Okay, no problem. Okay, so again, we can go through this. We'll start with the guy on the right. Why not? And by the way, you should start to see patterns that, regardless if they're in sort of different compounds, sort of the way the bond is to those atoms, they're going to end up with sort of the same formal charge no matter what the situation. So again, we saw this guy a couple times at this point. It's going to be 6 minus 1 half of 2, and that is going to give us -1. So typically, if you see that single bonded oxygen there, looking like that, is probably going to have a -1 formal charge. But obviously on an exam or something like that, you do obviously need to show it, the work. So if we do our triple bonded oxygen, don't see that too often, but we'll go with that. 6 minus our 2 minus 1 half. In this case, triple bond means 2, 4, 6 electrons that are there. And 6 minus 2, which is 4, minus 3. So that's going to be a +1 here on this guy. And now if we look at the triple bonded carbon, that's going to be 4 minus 0 minus 1 half of 8, which is 0. So in this situation, we got a -1 and a +1 and a 0 going on. If we look at the double bonded CO2, again, our double bonded oxygen going to give us 6 minus 4 for our non-bonding electrons, minus 1 half of 4 for our bonding electrons, which are our lines. And that's going to be 6 minus 4, which is 2, minus 2, which is 0. So this guy's going to be 0. This one's identical to it, obviously will be 0. And then we have our double bonded carbon, which would be 4 minus 0 minus 1 half of 8. And that's going to be 0 as well. So again, we can see here in sort of deciding these, and again, just in case you decided, hey, I want to like triple bond right out of the box there with CO2, this is the reason why, again, not the best choice to do that. Again, the double bonded version here gets us all zeros in terms of formal charge, and again, that is sort of your ideal situation in a structure. Any questions on that there? So obviously, like I said, you do need to be able to calculate the formal charge. You do need to be able to use the formal charge to determine maybe between two different structures, which one might be the better structure. Any questions on any of that there? Okay. All right, so we talked a little bit about resonance structure last time, but we'll get into that in just a second. But let's just talk a little bit about bond length, and we'll talk about bond strength in just a second. You obviously do not have to memorize any of the numbers that are on this chart or anything like that. It's just obviously for reference purposes of what we're talking about here. So for example, if we look at the carbon-carbon sort of single bond, double bond, and triple bond, this is the bond length. So this is the distance really kind of between the two nucleuses inside that bond. And we see that from the single bond, it has a distance of about 154 picometers, double bond 133 picometers, and a triple bond 120 picometers. So in general, what we're seeing here is as we go from a single bond to a double bond, the distance gets smaller. And as we go from a double bond to a triple bond, the distance gets even smaller. So we went from 154, put on another bond, everybody came in closer to each other. 133, put on a third bond, everybody came in closer at 120. We see that pattern happen as well, for example, here in the carbon-carbon nitrogen bond, and that's our single, our double, and our triple. And we do see that our single bond there is larger than our double bond and larger than our triple bond. So as you can see with these numbers, they're not like twice as long or, 3 times as long or anything like that. But the general pattern is every time you basically slap on a bond, all those electrons basically come in. And what it does is sort of contract the distance between the two atoms. And then again, if you pop in a triple bond, it's going to move everybody closer to each other. So sort of what does that do with something like bond strength? And the relationship between sort of bond strength and single bond, double bond, or triple bond goes sort of the opposite way. A triple bond is stronger than a double bond, and a double bond is stronger than a single bond. So I usually think about it in the sense of like a brand new pencil, right? You get like a brand new pencil right out of the box, right? It's nice and long, right? You can snap it, no problem. You take a couple of chemistry sort of exams, you're down to like a nubbin and eraser sort of thing. It's like that big, very hard to try to break that pencil in half, right? Because the distance between everybody is a lot smaller. Everything's held in a lot tighter. And that's sort of what happens again in the relationship between bond strength and bond length. So the longer the bond, which would be your single bond, is the weaker of the bonds. And again, strength increases as you go from double bond to triple bond. Same thing with length. Bond strength is not like, again, a double bond is not twice as strong, for example, as a single bond, or a triple bond is not 3 times as strong. But that's just the general sort of trend that occurs. So we talked about electronegativity. In case you forgot, I think these slides were a little bit out of order there, but again, electronegativity, as we talked about, is a really important aspect of bonding. And again, that's our general trend, as we talked about, up and to the right. Is more electronegative, with fluorine being the most. And again, those things should have been moved over. I think we talked about all this stuff already. So let's just review it again. These were our different types of bonding that we talked about, obviously. And again, we have our ionic bond, our polar covalent bond, and our pure covalent, or again, our non-polar bond. I guess it's good to review, I suppose, at some point. And remember that we use really the electronegativity to help us determine between the differences in a particular bond. And that's, again, what is referred to as bond polarity when we use those electronegativity values. And again, that's the one that we did earlier, where it was 0 to 0.4 is a non-polar bond, above 0.4 to below 2 is a polar bond, and again, above 2 is usually ionic bond, as we see here. All right. And we're going to talk about that, I think, in the next chapter. So we'll get into that, actually. So we kind of went through some of that, so we're going to skip that. All right. Let's then talk about actually bond energy. So we don't really talk about a lot of about energy in this semester, actually. But we'll talk a little bit about bond energy here. And bond energy helps us decide whether or not a reaction is sort of, you could use it to decide if it's exothermic. And I think we talked a little bit about this. Exothermic basically means heat and energy is released. And delta H, which is the enthalpy, is one way that we sort of look at heat and energy in a reaction. And if the delta H is negative, that implies that the reaction is exothermic. So heat and energy is being given off. And that's opposite of our endothermic, which is heat and energy is absorbed. And delta H values are positive in that case. So positive delta H value means endothermic, heat and energy is absorbed. Negative delta H means it's exothermic, heat and energy is released. So when we actually make bonds and when we break bonds, you know, they're either endothermic or exothermic. And for example, when we want to break a bond, so we have a bond that's together, they actually is endothermic. So those guys have to gain some energy. When they gain energy, they get enough energy to sort of wiggle apart from each other. Happens just like that. Not really, but sort of. And so when we do break bonds, energy has to be put in to allow them to sort of break apart from each other. And that's opposite when we want to go and sort of form bonds. When we want to go form bonds, basically everybody's out moving around. They need to release energy. So as they release energy, they kind of slow down, and that allows them to sort of come together. So bond breaking is endothermic type process, which would be positive in terms of energy. Bond making is exothermic, which would be negative. So we can calculate the delta H, or the enthalpy for the reaction, based on, so we can calculate the delta H based on bond energy. A little bit, but not a lot. It has a little bit to do with entropy and sort of the amount of disorder and order, but not to a big extent per se. You'll learn more about entropy in 200B. You talk about all that, along with really delta H as well. You talk about it as well. So basically, we want to calculate the delta H based on bond energy. We basically add up all the bonds that we broke, and we add it to all the bonds that we made. Because that's basically what's happening in a reaction, right? You have your reactants, you have your products. So as you go from the reactant side, you essentially have to break apart all those bonds. And then, right, in a chemical reaction, the only thing that happens is they reassemble on the other side in new bonds. So on the reactant side, we're breaking all those bonds. On the product side, we're making all those bonds. And basically, you just add up the total amount of energy to do both of those processes. And that will give you the delta H for the reaction based on what's known as bond energy or bond enthalpy. So let's take a look. I think we might have an example. So that's basically what I just said there. You could kind of add everything together. It's really like about accounting. You just want to make sure you get all the bonds. You don't miss any bonds. And sometimes it's good to draw the Lewis structure if you're not sure what something looks like. So for example here, I can't see that thing, but here's a table of bond energy. So we'll go with, I hope it's on the slide right now, but essentially what we would do is we would want to look up the value and think about on our reactant side what we're breaking. So in this particular case, we are breaking 1, 2, 3, 4 carbon hydrogen single bonds. And if you went to this table, if you could see it, I think it's 4 or something right about there. You would want the value of all 4 of the carbon single bonds. We're also breaking on the reactant side 1 chlorine single bond. So we want to add up all the energy that we can from the table here. We want to multiply by obviously how many of those bonds we're doing and add them up. On the other side, we're going to be making some bonds. So on the other side, we're actually making 1, 2, 3 carbon hydrogen bonds. We're also making 1 carbon chlorine single bond. And on this guy, we're making 1 hydrogen chlorine single bond. When you look at that table, or if you see that table or a table like that in your book, which you might be able to read maybe better in this one, there's obviously single bonds, double bonds, and triple bonds. So that's why it's important to make sure that you draw the structure if you're not sure, so you can know if what you're breaking is actually a double bond, single bond, or triple bond, because they will have different bond energy. So really what this bond enthalpy or energy is what we were just talking about, in the sense of a single bond is less strong than a double bond than a triple bond. So if you're dealing, say, with a carbon-carbon single bond versus a carbon-carbon triple bond, the amount of energy required to break that bond or even make that bond is going to be different. So it looks like they had some numbers here. So we really just want to kind of add up all those things. So overall, in terms of bond breaking, we're going to break 1 carbon hydrogen bond. And let me explain to you why they got only 1 carbon hydrogen bond here. That's because here we broke 4 of them, and here we made 3 of them. And remember that the energy is going to be the same on both sides. The only difference is it's going to be positive or negative. So basically, if you made 4 carbon hydrogen bonds at 4 times 414 kilojoules, which just comes from that table, and you made for 3 carbon hydrogen bonds is going to be 4 times negative 414 kilojoules. The net difference is 1 carbon hydrogen that you actually made. So that's why they sort of got rid of it. So in terms of breaking, the total amount of energy to break all the real bonds that were going to be there is 657 kilojoules. On the other side there, we have all of our sort of making. And again, they don't include the carbon hydrogen because they sort of did it all right here. The only difference is, again, bond making is going to be exothermic. So all these numbers from the table become negative. And then when we add both of those together, we get an overall delta H for this reaction of minus 113 kilojoules, which means that this reaction overall, based on bond energy, is exothermic. So there's sort of a excess of energy that's going to come out as a result of making and breaking these bonds in this reaction. So again, they sort of simplified it a little bit here in this problem. You could have, did the 4 carbon hydrogens, and again, you would multiply the 414 by it, and then on the bond making part, you could have done the 3 carbon hydrogens and multiply it by minus 414, and again, you'll get the same answer. They just sort of reduced it down. Any questions on that there? So again, really important to sort of break those things. Maybe you can see it here. Let's actually, let's switch to the other view. Maybe you can see it better in that one. There you go. Okay, at least you can kind of see it, I think. All right, why don't you give this one a go? So calculate the enthalpy of the following reaction. So calculate the delta H for this based on bond energy, and hopefully you could kind of see that table, I think, a little bit better. Okay, so let's see. So remember, you really want to just sort of keep track of everything. So on the reactant side, we're going to start breaking. So we're definitely breaking a hydrogen-hydrogen single bond. So again, if you go to the table here, looks like we got 436. So we're breaking one hydrogen-hydrogen single bond, and that is 436 kilojoules. We're also going to break a oxygen-oxygen double bond. So again, this is why it's important to know what those bonds are, because if you just see O2, you might think, oh, it's just an oxygen-oxygen single bond. So again, if you're not sure, you might want to quickly sort of sketch the Lewis structure to determine is it a single bond, double bond, or triple bond. So that looks like 498. And at that point, that is everything we're breaking. So if we just kind of add that up real quick, and I find where I stuck my calculator. There it is. So if we do that real quick here, we got 436 plus 498, 934 in terms of the energy to break kilojoules. On the other side, we do have a hydrogen oxygen here. And I got something in the way, but I'm assuming that's a hydrogen oxygen there. Let me just verify there. Because, yeah. So we're basically breaking, we're making. We got 2 of the hydrogen oxygen bonds. So right about there, 464 each. We do need to multiply that by 2 because we're breaking 2 of them. We're also making 2 of them. And then also important, what a lot of people will forget, especially if they don't draw the Lewis structure and they just go off the actual chemical formula, they oftentimes will forget that center sort of bond. So that bond between our 2 oxygens there. And that's actually a single bond. So as you can see is a different value. So that's 142. So 1 oxygen at 142. And if we add all that together, that is 2 times 464 plus 142 gets us 1070. Now remember that when we break bonds, it's endothermic, so this is all positive. And when we make bonds, it's exothermic, which means technically that's all negative there. So again, you got to make sure you get the sign correctly. Technically, all these values here would be negative values. And if we add those together now with the correct signs, that's 934 plus a negative 1070. It's going to give us an overall delta H equals, again, 934 plus negative 1070. And that's going to give us minus 136 kilojoules. So what this tells us is the delta H of this reaction is exothermic based on the bond energy. Any questions on how to do that? Yeah, so in terms of energy, there's 2 signs really when you think about energy. If you have an energy sort of value, and usually delta H is what you're looking at, which is the enthalpy. If the delta H value is positive, it means it's endothermic. And if it's negative, it means it's exothermic. And when we break bonds, because they're together, they have to gain energy, which is endothermic, for them to get enough energy to break apart. And that's why the breaking part is positive numbers, because it's endothermic. Now, when you make them, since they're separated from each other, kind of moving around, they need to lose energy or give off energy to kind of slow down enough to sort of come together and make that bond. So when we make bonds, it's an exothermic process, and that's why those guys end up with a negative value. In the table, they're all going to be positives. And when we talk about energy, or we really want to talk about energy in this class, but the idea of energy that we talked about a little bit was the idea of conservation of energy. And basically in most processes, when we talk about energy, the actual numerical value of the energy as it's moving from one place to the next is actually the same. The only difference that changes is whether it's positive or negative to imply that it's endothermic or exothermic. So for example, if you have a reaction in a beaker and that reaction starts to give off energy to the surroundings, if that reaction lost or gave off like 200 kilojoules of energy, for the reaction, it would be negative 200 kilojoules of energy. But for the surroundings, which picking up all that energy, is going to be positive 200 kilojoules. So numerically, the value will be the same. The negative or positive helps us understand the flow of the energy. Is it leaving or coming in? Yeah, so it's pretty much that simple as well in terms of delta H. Pretty much, if you're really only interested in whether or not the reaction is exothermic or endothermic, you could care less about the actual number value. It's actually the sign that's the most important. So if you see that negative for delta H, it's exothermic. If you see a positive, it's endothermic overall. Which in a lot of cases is sort of what you're interested in, is whether or not it's exothermic or endothermic. So that sign is really a big part of it. Other questions on that there? Oh, there it is. There's the answer in a much prettier picture, but works the same way as what we got, which is good. All right, so let's talk a little about resonance structures, which we kind of did already when we were going through drawing Lewis structures. But resonance structures, again, are those structures that you could draw when there's really kind of more than one option. In a lot of cases, in terms of where you could place, for example, a double bond. So for example, like SO2, you could double bond on the left, you could double bond on the right. CO3, 2 minus, you could double bond up on top, to the left, to the right. So you can draw multiple sort of structures for certain things, especially double bonds, even maybe triple bonds in certain cases. And we draw resonance structures because really one structure doesn't adequately describe sort of its really orientation or structure. Again, those double bond electrons are kind of delocalized, so they're able to sort of move around from sort of one atom to the next in a molecule, and that's why we get these different resonance structures. So our ozone, as we saw earlier, again, you could double bond on the left, or you could have double bonded on the right. Again, they're both equivalent structures to each other. And if you were asked just to draw the Lewis structure for ozone, you don't necessarily have to draw all the possible resonance structures. You just need to draw one or the other. Again, you would only need to draw resonance structures if they told you draw all the possible resonance structures. This is our carbonate that we saw as well earlier. Again, the main difference between them is the location of that double bond. And you'll even sometimes, you'll see in books, people will illustrate that almost like this. They'll sometimes do like a dotted sort of line to illustrate that those double bond electrons can be moved from one side to the next or sort of delocalized. The benzene ring, it's more of an organic molecule, looks something like this. It has 3 double bonds, and sometimes you can move those double bonds to the other side. Looks something like this. And sometimes benzene will just be drawn like this to indicate that, you know, there's a resonance structure. And organic, sometimes they'll just draw like a little circle in there, again, to indicate that those electrons can be moving around from one spot to the next. And we'll just go through this one. That's okay. Here's a whole bunch of different ones you could draw for this particular guy. So again, as we talked about, resonance structures, you don't necessarily have to draw all of them, only if the question specifically asks you to draw some. But again, that does give us some different sort of possibilities in terms of what a structure may look like in terms of Lewis structures. Now, we talked about the octet rule, that is sort of the defining principle, if you will, for when you draw these Lewis structures. But you know, you were usually beat into your head sort of in maybe the previous class that, you know, never go over 8, never go over 8. But there's actually a lot of exceptions to the octet rule. And in this particular class, we will see a number of exceptions sort of occurring. So let's talk about some of the different exceptions to the octet rule that we sometimes come across. And the first one is what is known as an incomplete octet. So an incomplete octet basically means pretty much what the name implies, that you have less than 8 valence electrons. So there are certain things on the periodic table that are, perfectly fine with less than 8 electrons. And although beryllium hydride maybe doesn't truly really exist because it's like a metal non-metal situation, um, boron is the most sort of common guy that you see. Boron is very much a element that will go less than 8, and usually will hit about 6 like we have here with BF3. And in that particular case, boron is perfectly fine in that situation. Again, because it has that incomplete octet, is what is sometimes referred to as being electron deficient, because it doesn't have the traditional 8 electrons around it. So it's deficient. It actually makes it actually a really good, what is referred to as a Lewis acid. And we learn that in the next class as well. But it actually makes it a really good one to be able to sort of accept electrons, because it hasn't really maxed out in terms of 8 electrons, and is sort of comfortable with 6. And it has the ability actually to react with certain things in a sort of acid-base way that makes it really well. But I would say for an incomplete octet, you should know boron, and boron typically is your guy that will kind of go less than 8. Another exception to the octet rule, and there are 2 exceptions. Oops. Let's start with this first one, and that's an odd number of electrons. And what that means is when we've done our total number of valence electrons, when we go to draw our Lewis structures, we usually end up with a nice pretty number where everybody pretty much pairs off. We could put all those electrons on in pairs. And there is a situation where you would get a odd number, and because you get an odd number, when you go to draw the Lewis structure, you will actually end up with an unpaired electron, which is what we see here. And in NO and NO2 here, you do end up with one unpaired electron. And that one unpaired electron is sometimes what is referred to as free radicals. So there's a lot of chlorine guys in atmospheric chemistry that are one electron only, or has one unpaired electron. And that's really not the situation that they want to be in. And what that means is these guys are usually very, very reactive because of that, because, they're kind of looking to pair off that electron, if you will. So that makes them very, very reactive because they do have sort of that one unpaired electron. So 2 exceptions, an incomplete octet and an odd number of electrons, are 2 exceptions to the octet rule. And now we come to the 3rd exception to the octet rule, which is, pretty much the one that we see 98% of the time, I would say, 99% of the time here. So out of all these 3 exceptions to the octet rule, for this class, this is the one that you'll probably run across the most. And this is what is known as an expanded octet. And an expanded octet means, just like it sounds, it could actually go over 8 electrons. And it can have upwards of 10 to 12 electrons around a particular element in a Lewis structure, which means usually it could have upwards of 5 or even 6 bonds that can pretty much occur. So pretty much if you look at the periodic table, there is a location on the periodic table where we typically do see this effect occurring. And that is where we see, if you look at the periodic table, and right about here is our good friend sulfur. And sulfur, if you go to the right of sulfur and you go to the left of sulfur and you go down from sulfur, mainly in the non-metal region, since this is usually where we're talking about non-metal. Yeah, so we're going to talk about that actually right now. Is what we're going to answer your question actually. So if you go to the periodic table and you find sulfur and you go to the right, like I said, and you go to the left and you go down, And like I said, usually in that non-metal region is where we're talking about. Remember, the staircases kind of come in, you know, through here as well. Those guys have the ability to do the expanded octet. So if you look on the periodic table where sulfur is, you will see the sulfur is in row number 3 on the periodic table. And that means that the N value for that sulfur and those guys near sulfur is N is equal to 3. And if you remember when we talked about N equals 3, that is the third energy level. And on the third energy level, that is where we first start to see d orbitals appear, right? So that is where we first start to see actually d orbitals appear. Remember, on the third energy level, you have s orbitals, you have p orbitals, and you have d orbitals. And that's the first energy level where d orbitals actually do start to appear. Now, even though something like sulfur, for example, does not technically use their d orbitals in a normal situation, they still have d orbitals available to them. And that is why they're able to stash all those extra electrons and go over 8, because that is when we first start to see d orbitals appear. So right there at sulfur and down, and a little bit to the right and left and down, they have those d orbitals available to them, even if they're not using them. And that gives them really sort of, if you want to think about it, a physical location, I guess, to sort of stash some extra electrons. So to sort of answer your question, elements around sulfur and down can go above 8. That also means, though, if you back up on the periodic table to period number 2, like where we have carbon, nitrogen, oxygen, you know, all those guys there, fluorine. Those guys in period number 2 is N is equal to 2, which only have S and P orbitals available to them. That means that those guys like nitrogen, oxygen, carbon, all those guys, they should never ever go over 8 because they don't have the ability to do so. So those guys in period 2 above sulfur, they actually have to obey the octet rule always because they don't have those d orbitals available to go above it. But once you get down to sulfur and to the left and to the right and down, they do have that ability to go above it. And this is also where we can kind of tie in the formal charge that we were just talking about earlier to help us decide that, you know, maybe it's better in a certain situation that sulfur or somebody near there, you know, makes an extra double bond versus a single bond. And we'll talk about that in just a second here. But an example of that, for example, would be SF6. And if we looked at SF6, for example, and we drew it, sulfur is 6 plus 6 times 7 there for our fluorines. And that is, what is that, 42, 48 electrons. So it would be the same idea. We would go with our sulfur here in the middle. We would have our fluorine, lots of fluorines, 6 of them per se. We would make one bond just like we did before. That's a lot of electrons, 2, 4, 6, 8, 10, 12 electrons. We'd fill up all the outside ones. So that is 1, 2, 3, 4, 5, 6. 6 times 8 is 48. And it would be perfectly good here. Yes. And as you can see, when we look at the sulfur, it actually has 2, 4, 6, 8, 10, and 12 electrons around it, which makes it perfectly okay. They are. So when we're talking about that, though, so just to be clear, you are right in that sense. The sulfur is in what we refer to as the P block. And really what that means in terms of electron configuration, that's where these guys will kind of end their electron configuration. So he'll be like 3p, 1, 2, 1, 2, 3, 4. So he'll end his configuration as 3p4. And that's why it's referred to as the p block in that area, because that's where they end their electron configuration. And you're correct, when you get down to, say, 21 there, you know, you have 4s1 and 3d1, right? And that's the d block in the transition metal. And again, this referred to as the d block in the transition metal because their electron configurations basically end in the d's. But what's important to remember is 3p, right, 4, this first number is the quantum number, right, that n number. And n equals 3, which means technically on the n equals 3 level, you can have values of L of 0, 1, and 2. And that is an s orbital, right? A p orbitals are available, and also the d orbitals are available. So again, even though sulfur technically in a normal situation is not using those d orbitals, they are still available for them to be used. And that's just how they can use them in a different application. But if you just have sulfur by itself, it's going to top out in terms of filling electrons, you know, with the S's, and then top out there at the P's. Again, technically, because it's on the third energy level, even though they may not be using them, they still have the D's available to technically use. Yeah. But so when we say the sort of P block, the D block, again, that doesn't necessarily mean that's again where, you know, those orbitals sort of, that's their only orbitals available to them, but it means sort of in terms of filling the electrons, that's sort of where the electron configuration sort of stops. Other questions on that? So to sort of tie this together with sort of the formal charge and, you know, the ability of certain elements to go above 8, let's take a look at a very common one that people see, and a very common one, you know, people Google and write down on their paper and don't really understand why they do that, but they see it when they look online. Not good to do that, by the way, but, you know, some people do. It's good to understand, I suppose. Let's take a look at sulfate. And if we do sulfate, this is 6 plus 4 times 6 plus 2, again, for our electrons here, if we're going to draw it. So that's 24, 26, 32, I think, on that. So if you follow the rules like we talked about in sort of drawing the Lewis structure for sulfate, you'll have your S, you'll have your O, you'll have your O, you'll have your O, you'll have your O. And we do our one bond to everybody. That's going to be 2, 4, 6, 8. So it's going to be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 32. I think I lost count there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So that is all 32 electrons. And if we look at that again, you would want to make sure everybody's hit the octet rule. And if you go around to all the oxygens, that is 8 around it. The sulfur has 8. So this is definitely an acceptable structure for sulfate. And some people will say, well, I've seen it like double bonded. So some people will see sulfate drawn like this move, for example. Not sure why it's tilted there. We'll just assume it's straight. We'll go that way. Ignore the tilting of sulfate there in the structure. All right. So you'll sometimes see sulfate drawn like this. And that also could be a very good structure as well. So what can help us determine, you know, which structure may be better in this case? Again, they both, you know, sort of meet the octet rule. Obviously, in this case, sulfur goes expanded octet versus sulfur with no expanded octet over here. So this is where we could use formal charge to help us. So if we did the formal charge on our oxygen like we did before with a single bond, we would have our 6 minus 4 minus 1/2 of 2 going to give us, where are we at there? 6. I'll learn to count there. That's 6 minus 6. There we go. There's 6 non-divided electrons. Gives us a -1. So again, like we saw before, this oxygen has a -1. This one's the same. It will have a -1. This one is the same. It will have a -1. And this one's the same, which will have a -1. Now the sulfur in the middle, where we're all single bonded, would be 6 minus 0 minus 1/2 of 8. And it's going to switch back to the other view real quick since I'm doing too much writing, I think, for the slide. Go back that way. Okay. So at this point here, we have 6 minus 0 minus 1/2 of 8 is going to give us +2. So the sulfur here in the middle has a +2 formal charge in this configuration. Still adds up to -2, right? So -4 on the outside plus 2 gives us -2. Now, if we go to the structure where we double bonded it, what we will see is, again, the oxygen with a single bond will come out the exact same as what we just did over here. So that's going to be -1 and -1. Our double bonded oxygen will come out the same as we saw previously, 6 minus 4 minus 1/2 of 4, and that's going to give us 0. So this guy is 0, this guy is 0. Now our sulfur in the middle, where it was double bonded and single bonded, expanded octet. I can go up here and do that. So the expanded octet is going to be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 2, 4, 6, 8, 10, 12 gives us 0. So if you ended up with these two structures or drew these two structures based on formal charge, which one would be the correct one, do you think? Should it be the one on the left or the one on the right? The better structure is actually going to be the one on the right, where we double bonded. Again, we can see that we have 3 zeros in terms of formal charge. We have the -1s on the oxygen, which is really good. If we go over to the guy on the left, it is not as good of a Lewis structure because, first off, we have a pretty big positive charge, formal charge, on that center atom of +2. So if you remember, things with +2 or +3 are not as good as, things with lower formal charges. And obviously, that's a major difference. So by making bonds with sulfur, by making those double bonds with sulfur, we were able to bring down the formal charge of that central atom down to 0. And that makes for a much better Lewis structure than the guy on the left. For our class, if you're not asked to draw the Lewis structure based on formal charge, you don't have to worry about that. You could draw either structure. But this is why commonly, if you kind of online or look around, you will commonly see sulfate drawn more like what we see over here. And that's because based on formal charge, that would be a much better structure than the guy on the left. Any questions on that? So again, this is sort of that practical application of formal charge where, you have a couple different options maybe as to how you could draw your Lewis structure, even to the point where we're talking about differences in how many bonds we're making. And you could use that to help you decide a better structure over maybe a not so good structure. Again, both would probably be acceptable in most situations. But if you were again asked to draw the structure based on formal charge, you really should draw the one on the right because that's a better structure. Question on that? All right, so just to finish up here, I'm going to give you a few to draw to make sure. Why don't you draw, or a couple to draw? Why don't you draw BrCl5? And why don't you draw, we'll try ClI3. So draw those two Lewis structures. They hopefully should be expanded octets if I didn't mess up, hopefully. Okay, so since we're getting to the end, let's take a look here. So you want to follow the same approach. So 7 for the bromine. There's 5 chlorines also at 7. That's a lot of math there. 35 and 7, and go with 42. So again, we just want to kind of follow the same steps. So obviously we only have 1 bromine and 5 chlorines. Bromine is least electronegative, should be in the middle. And some CLs around. And again, wherever you want to kind of pop that 5th one, I'll go up here. We're going to do 1 bond in, just like normal. And that's 2, 4, 6, 2, 4, 6, 8, 10 electrons. Gives us 32 more to go. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So at that point, I have now put on 1, 2, 3, 4, 5, and 8 is 40 electrons. I still have 2 more to go. And just like normal, those 2 will actually end up right there on the center atom as pairs. So that should be 42 electrons, I think. And again, everybody's met the octet rule. Bromine has gone above the octet rule, but if you look on the periodic table, bromine is down and to the right of sulfur, which means it has the ability to do that. Any questions on that particular one? Now let's look at the next one, which is chlorine is 7, 3 iodines also 7, and that is going to be 21, 28 valence electrons. Same deal here, chlorine and iodine. We're going to put chlorine in the middle. Again, there's only 1 chlorine, so it is going to go in the middle in this case. And we're going to go this way, and this way. This would have been a better example. Actually, if I used F, would have been a better move, but we'll pretend here in this case. Iodine here, 2, 4, 6. Then we want to go 8, 10, 12, 14, 16, 18, 20, 22, 24. And at that point, that's 24. We still have 4 more to go, which would be 26 and 28. And just to make it a little bit better and more correct, we'll go with F, because F is more electronegative. We'll just turn them into fluorines. Comes out the same. But here again, we can see all the F's that I just converted into 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. And again, we just end up with some extra kind of dots on there. Any questions on that there? So expanded octet is really the one we'll see a lot in this class. And the good news, bad news is, there's like a whole bunch of geometries that go with these expanded octets. So we'll get into that in the next chapter. And if I'm not mistaken, I think that should wrap up this chapter. Yep. Any questions on any of that stuff there? So obviously you need to be able to draw Lewis structures, exceptions to the octet rule. And I say in our class, probably just this one, the expanded octet is probably the one you have to worry about. Any questions on any of that? Okay, a couple of things. We have lab today. So we're going to do the hydrate, which is our first formal experiment. So we're going to talk about sort of the formal experiment, look over some stuff in terms of the lab report that will be due for that. In addition, we'll talk a little bit about the exam, which again, a reminder is coming up on Monday. Also, we'll talk about the practice sort of quiz that I made, which will be available in about an hour or so, but you could take it anytime between now and like Sunday. And we'll talk a little bit about that and sort of how you should approach that one so that you'll be prepared hopefully for Monday and the exam. Again, the exam will cover chapters 1 and 2. And again, we'll talk more specifics at the beginning of lab. So we'll see everybody in lab in about, 9:30. So, and we'll do about 9:50 since we ran a little bit long here. So we'll start lab about 9:50, come through the lab link. And again, make sure you wrote here in the chat if you have not done so already.